In today's class, we will discuss about the phase shift of symmetrical components in a star-delta transformer bank. So, star-delta means primary star side, secondary is delta side. Okay. So, if you take a core type transformer, there will be single phase core type transformer, there will be two limbs. Okay. So, in one limb, half of the primary winding and the half of the secondary winding will be wound. So, similarly, in the second limb also, remaining half of the primary and the remaining half of the secondary will be wound. Okay. So, this type of winding, see, all the primary winding will not be done on one limb. Similarly, all the secondary winding will not be done on the second limb. Half of primary, half of secondary in one limb and half of primary and the remaining half of the secondary on the second limb. So, this type of winding is done in a transformer to reduce the leakage. Okay. So, the same magnetic flux will link with primary as well as the secondary winding. Okay. So, the EMF induced in the primary and secondary winding will not have any phase shift. Okay. But this is not the case in the case of the sequence components of the voltages and currents. Okay. So, in the case of a transformer, since both windings, primary as well as secondary, are wound on the same limb, half of primary, half of secondary, the same magnetic flux is going to cut both the windings. So, there will not be any phase shift. But this is not the case in the case of a sequence components of voltage and current. Okay. So, hence, the positive and negative sequence voltages and currents undergoes a phase angle change while passing through a star-delta transformer. So, this is called as the phase shift. Okay. So, let us derive the voltage relation as well as the current relation of the sequence components. So, first is voltage relation. So, let us consider a transformer connection. The primary is star, secondary is delta. So, in the secondary side, what I have taken is the star equivalent of the delta is also shown. Okay. So, primary is completely star. So, we have taken EAS, EBS, ECS as the phase voltages on the star side of the transformer and E capital A D, E capital B D, E capital C D as the phase voltages across the windings on the delta side of the transformer. Okay. And we have also drawn the star equivalent on the delta side. Okay. So, we have taken EA small d, EB small d, E small c d as the phase voltages on the equivalent star on the delta side. Okay. So, here the superscript S refers to the star and star side and superscript D refers to the delta side. Okay. Yeah, as I told already, the voltage across the various windings wound on any core will be all in phase because the voltages are induced due to the rate of change of magnetic flux in the same core. Okay. So, the phase voltages on the primary side should be in phase with the voltage across the corresponding phase winding on the delta side. Okay. So, if N is taken as the turns ratio of the transformer. So, there is a difference between transformation ratio as well as the turns ratio. What is turns ratio? Primary number of turns by secondary number of turns. What is transformation ratio? Secondary by primary. So, here we are taking only the turns ratio. Small n is equal to N1 by N2, which is also equal to E1 by E2, which is also equal to I2 by I1. So, here you should be very careful. Okay. So, using this turns ratio n of the transformer, we can write the relation between the phase voltages on the star side as well as the delta side. Okay. So, now star side is the primary, delta side is the secondary. So, what is n? Primary by secondary turns. Okay. So, n is equal to EAS by EAD, star by delta. Okay. Phase voltage of the E1 by E2, phase voltage on the primary star side divided by the phase voltage on the secondary delta side. Okay. So, EAS is equal to N into EAD. So, in the same way, we are writing for the other two phases also, EBS, ECS. Okay. Now, we are relating using the sequence components. Okay. So, the positive sequence component, negative sequence component and zero sequence component can be written for phase A using these relations. Using this set of relations, We are writing the positive, negative and zero sequence components of phase A voltage alone. So EA1S is equal to NE capital A1D. EA2S is equal to NE capital A2D. Similarly, EA0S is equal to NEA0D. So in the previous lectures, we have seen that the zero sequence component will be equal to 0. Okay, so that's why I have written EA0 is equal to 0. So now the line voltages on the delta side of the transformer are equal to the phase voltages on the delta side. So we know that for a delta system, line voltage will be equal to the phase voltage. Okay. So but the phase voltage of the equivalent star on the delta side are different from the line voltage. Okay. So remember, in the secondary side, we have converted the delta to equivalent star. So in that equivalent star, the phase voltages will be different from the line voltages. So now we are defining, as I told already, E small a d, E b d, E small c d as the phase voltages of the equivalent star on the delta side. Okay. So already in the case of the derivation for a star connected system, we have derived these two relations. So the line voltage, positive sequence component of the line voltage is equal to J root 3 into positive sequence component of phase voltage. Negative sequence component of line voltage is equal to minus J root 3 into negative sequence component of the phase voltage. Okay. So using this relation, we are writing for our secondary side. Okay. So which is the delta side. Okay. So E capital A1D is equal to J root 3 E small a1D. So what is E capital A? It is the line voltage on the delta side, which is equal to the phase voltage. What is EA1D? It is the phase voltage on the equivalent star on the delta side. Okay. So in the same way, we are writing E capital A to D is equal to minus J root 3 EA to D. Okay. So now what we are doing is, we are going to substitute. We have marked the equations, sequence component equations as 1, 2 and 3. Okay. And these two are taken as equations 4 and 5. Now substitute 4 in equation 1. So equation 1 is EA1 is equal to NEA1D. So on substituting equation 4 in 1, you will get EA1 is equal to J root 3 N EA1D. Similarly, substitute equation 5 in equation 2. Equation 5 in equation 2, you will get EA2S is equal to minus J root 3 N into EA2D. Okay. So here, what is EA2S? What is EA2S? It is the phase voltage on the, primary star. What is EA2D? It is the phase voltage of the equivalent star in the delta side. Okay. So these terms you should be very, very careful about. Okay. So now we can arrive at a conclusion that positive sequence, consider this equation, positive sequence component of the phase voltage on the star side leads, because we have J, the corresponding positive sequence components on the delta side by 90 degree. Okay. So in the same way, negative sequence components of the phase voltages on the star side lags, because it is minus J, lags behind the corresponding negative sequence components of phase voltage on the delta side by 90 degree. Okay. Now we can draw the phasor diagram for this statement. So positive sequence component phasor diagram, A, B, C sequence. What is EAS? It is the EA1S, it is the positive sequence component of phase voltage on the star side. Okay. So now you look on to this, how I have drawn on the equivalent star on the delta side. Equivalent star on the delta side. So we know on the star side, this is on the delta side. Okay. So star side is leading by 90 degree. So see, this is A. Here you should draw like this A, exactly 90 degree. So this vector should be 90 degree with respect to this vector. Similarly, this vector should be 90 degree with respect to this vector EC1S. Similarly, draw this exactly 90 degree with respect to this. Why? Because in this statement, EA1S leads EA1D. So EA1S is ahead of EA1D by 90 degree. Okay. So it is leading. Okay. Then followed by EA1D. Similarly, see EB1S is leading, but this is lagging behind EB1 by 90 degrees. Okay. So in the same way, you can draw for the negative sequence components also. Okay. So while drawing for the negative sequence components, you should be very, very careful. See, we know the phase sequence for negative sequence is ACB. ACB, ACB. Okay. But to get the positive sequence ABC, we have to rotate the set of phasor along the clockwise direction. So if you rotate along the anti-clockwise direction, you will get ACB. Okay. So, but ABC is the positive sequence. Okay. So, rotate along the clockwise direction to get the ABC sequence, balanced phase sequence for a balanced three-phase system. Okay. So, now let us consider only this EA2S, negative sequence component of phase A on the star side. Okay. So, EA2S, what is EA2D? It is the negative sequence component of the phase voltage of the equivalent star on the delta side. So, this EA2S should be lagging behind EA2D. So, now if you rotate along this ABC sequence clockwise direction, what you will get? EA2D is leading, followed by this EA2S. Okay. So, in the case of negative sequence components, EA2S lags behind EA2D by 90 degree. So, see, each vector corresponding phasor is drawn at an angle 90 degree with respect to each other. See, this C and this C 90 degree, this B and this B 90 degree, A and A 90 degree. But you should be very careful which one should be lagging. So, here star side EAS2 should lag behind the delta side. Okay. So, this is going first 90 degree followed by this EA2S. Okay. So, in the same way, we can arrive at the current relations. Phase shift in the case of currents on both the star and delta side. So, let us consider this connection. This is star connection. This is the delta connection. So, IAS, IBS and ICS are the line currents. And you know, in the case of a star system, line and phase currents will be equal. So, coming to this delta side, the phase currents are I capital A, D, I capital B, D, I capital C, D. So, phase currents are nothing but the current through the phase windings. And what are the line voltages on the delta side? IAD, IBD, ICD. Okay. So, that's what we have defined over here. So, in terms of the turns ratio, we can relate the primary side as well as the secondary side phase voltages. So, what is this small IAS? Line currents in the star side. What is I capital AD? So, this will be equal to the phase currents also. Okay. So, what is I capital AD? The phase currents in the delta side. So, we are relating the phase currents on the star side as well as the delta side using the turns ratio. What is turns ratio? I2 by I1. Okay. So, IAD by I small a s. Delta side is the secondary current by primary current. Okay. So, in the same way, we are writing for the other two phases also, B phase and C phase. So, now in the delta, we have three nodes, node A, B and C. So, write KCL equations. Write KCL equations for the three nodes. So, if you write KCL equation for node A, IAD, it's outgoing, IAD plus ICD is equal to IBD. So, remember phase voltages are capital A, B and C. So, I small a d is equal to I capital BD minus I capital C D. Okay. So, substituting for the relations in terms of turns ratio, what is IBD? N into IBS. What is ICD? N into ICS. N is common, IBS minus ICS. In the same way, we have written the KCL equations for node B as well as node C. And we got this equations. Okay. And for positive sequence components, now we are writing only the positive sequence component of phase A current. Okay, so IA1D is equal to N into, consider only this equation. IA1D is equal to N into IB1S minus IC1S. Okay, and in the initial lectures we have seen, if we have IB1, how to get IA1. So rotation of IB, IA1 twice along the anticlockwise direction will give you IB1. Similarly, rotation of IA1 one time gives you IC1. So IB1 is nothing but A square into IA1. IC1 is nothing but A into IA1. So now this IA1S is common. So A square minus A, you take it outside, and we have already arrived at A square minus A, which is nothing but minus J root 3. Okay. So we got IA1D is equal to minus J root 3 and IA1S. Okay. So we are writing the primary sequence component of current on the sequence component of phase A current on star side. Primary side is equal to J divided by N root 3 into the IA1 on delta side. This is primary side, this is secondary side. In the same way, obtain this equation for the negative sequence component of current. IA2D is equal to N into IB2S minus IC2S. And what is IA2? IB2? It is A into IA2. What is IC2? A square into IA2. Okay, so taking this common, IA2 as common, we get A minus A square. What is A minus A square? J root 3. So we can write the negative sequence component on the star side, primary side, is equal to minus J N root 3 divided by N root 3 into IA2D. So what is the inference made? The positive sequence component of the current on the star side leads the corresponding positive sequence component on the delta side by 90 degree, because we have plus J. Okay. So the positive sequence component of line current on the star side leads the positive sequence component of current on the delta side by 90 degrees. Similarly, the negative sequence component of line current on star side lags behind the corresponding negative sequence component of the line current on the delta side. Okay, so IA represents the line current on the star side. IAD represent the line current of phase A in the delta side. Okay, so this is what you have to write for phase shift in star delta transformer bank.